In experiments, scientists found that some molecules are more stable than expected. Suppose A and B are different atoms. A and B form homoatomic molecules A2 and B2, and heteroatomic molecules AB. It is found that twice of the dissociation energy of AB is greater than the sum of the dissociation energies of A2 and B2. Here, you can see an example of hydrogen and fluorine. This phenomenon cannot be explained by simple overlap of atomic orbitals. The reason of this stronger bonding between different atoms is that atoms have different abilities to attract electrons towards themselves. When different atoms bond together, the electrons are biased to one of them. Thus, one of the atoms is positively charged, while the other atom is negatively charged. As a result, there is an electrostatic attraction between the two atoms. The electrostatic energy between atoms increases to the dissociation energy of the bond. The electronegativity is the physical quantity to describe the ability of an atom to attract electrons towards itself. In Pauling scale, the value of the electronegativity of an atom is the ability of an atom to attract electrons towards itself in molecules. The difference in Pauling electronegativities between two atoms is defined by this equation below. Pay attention, electronegativity in Pauling scale is dimensionless. The electronegativity of hydrogen is defined to be 2.2. Thus, the electronegativity of other atoms can be measured and calculated. For example, the electronegativity of fluorine can be calculated from previous data. In general, atoms with high ionization energy and high electron affinity usually have high electronegativity. That is, the elements on the northeast corner of the periodic table have higher electronegativities. Fluorine has the highest electronegativity of all elements. In contrast, the elements on the southwest corner of the periodic table have lower electronegativities. When atoms with different electronegativities bond, the electrons are biased to the one with higher electronegativity. If the difference in electronegativities is smaller than 0.5, the charge bias is not significant. Such bond is called nonpolar bond. For example, the carbon-hydrogen bonds are nonpolar. If the difference in electronegativity is between 0.5 and 2, the charge bias is quite significant. Such bond is called polar bond. A polar bond has an electric dipole moment. For example, chlorine-hydrogen bonds are polar, so the hydrogen chloride molecule has an electric dipole moment. The chlorine atom is negatively charged because it is more electronegative, while the hydrogen atom is positively charged. Thus, the direction of the electric dipole is from the chlorine atom to the hydrogen atom. Both nonpolar and polar bonds are called covalent bonds because their bond energies are mainly contributed by the orbital overlap. If the difference in electronegativities is greater than 2, the bond is called ionic bond. Ionic bonds are typical in salts such as sodium chloride and ammonium nitrate. In an ionic bond, one or more electrons are biased, so ions are formed. In ionic bonds, electrostatic interaction has more contribution to binding energy than orbital overlap. But pay attention that all ionic bonds still have some degree of covalent bonding.